2 of our lecture about the geostrophic wind, and when last we left, we were making the painful realization that our puny human brains are just not good at looking at certain kinds of things like 3 vectors and trying to figure out just with your eyeball if they cancel out. Do they add up? It's just not the way human brains work. We're going to need a better way to do this. And if we went back and took a look at our list of the forces that are acting on the atmosphere, well, we had been keeping hold of 3 of them before. But what if we threw one of them out? What if we said we'll just consider 2 forces? Let's just do that first, and then we'll decide if we can figure out what to do with that 3rd force. Alright, so I'm going to put a little check mark here. I'm going to say let's work with the pressure gradient force and with the Coriolis force. In other words, for right now, I'm saying let's not worry about friction. Maybe that's a good I don't know. Well, there certainly are going to be parts of the atmosphere where we can not worry about friction, like outside of the boundary layer. Up above the top of the boundary layer, that is to say, the free atmosphere, friction is actually not really a thing. And so, okay, this is not so bad. So now if I only have 2 forces to work with, and I want these forces to add up to 0, well, now adding up to 0 is easy to think about. I mean, how you take 2 vectors and you add them up to 0 means that those 2 vectors have to be equal but opposite. So whatever I have for a pressure gradient force, like that red vector in that case, again, I'm just throwing a vector on there. It could be any number of different directions. That's the direction I just happen to pick. And then my Coriolis force has to be equal but opposite. It is not difficult at all to think about that. Human brains can do that pretty well. Equal and opposite is something we have lots of experience with in our day-to-day life. So if these are the only 2 forces that we're going to worry about as being affecting this air parcel, and they're equal but opposite, means the net force acting on that air parcel is 0. And by Newton's, by the definition of what we mean, that's by Newton's 2nd law, we know then that the acceleration on the object is 0, in this case on this air parcel. No acceleration on the air parcel means that the velocity is not changing. dv dt, the change in velocity with respect to time, is equal to 0. So the velocity is not changing. We're saying whatever the velocity is, it's just going to do that and just keep doing it. I hope that makes you uncomfortable. That doesn't sound right, does it? It doesn't sound like we should be able to say that, like, we're going to be making this assumption that the wind's not changing. Good. That should make you unhappy. On the other hand, it kind of depends on what time frame we're talking about. You're right. Whatever the wind is doing now, presumably tomorrow it's doing something different. It is changing. Perhaps even an hour from now it's doing something different. Heck, maybe even a few minutes from now it's doing something different. But can you see, if we zoomed in enough, we could eventually say, okay, yes, it's not going to change much over the next few seconds. Heavens, it's not going to change much over the next second. Okay? If we kind of look closely enough over a short period of time, this idea that the wind isn't changing, I think I can live with it. Okay? It's not going to work over long periods of time, but you know what? At least like kind of an instantaneous sort of way, like right now, you could kind of say, well, the wind's going to be the same for at least the next second or so. Okay. That's a fancy, no, kind of the opposite of fancy. That's kind of a stupid way of saying that this is a diagnostic equation. This is going to be, this geostrophic wind stuff that we're heading toward is a way of describing what the winds are doing right now, not talking about how the winds are changing. But that's okay. So we kind of have specified that the winds aren't going to change. That's no problem. And notice that in order to get to this really simple situation with the 2 forces that are equal but opposite, we had to get rid of friction, which is only going to be okay above the top of the boundary layer, up in the free atmosphere. Remember, the top of the boundary layer is what, about a kilometer or 2 up. So for most of the atmosphere, this is actually not a very bad assumption whatsoever. Kind of a bummer in a class about wind power, though, because wind power is all generated down here in the boundary layer, but we're using this idea, we're working our way toward a way of explaining what the winds are going to be doing closer to the surface, where friction is going to matter more. So if this is going to be this balance of forces that's going to be acting on an air parcel under some kind of conditions like friction not mattering, what can we actually say about how that air parcel, that little blue circle right there, how it's moving? Well, if my green arrow there is the Coriolis force, I guess I kind of already know which way the air parcel is moving, because we know the Coriolis force has to be oriented 90 degrees to the right of the direction of motion. So apparently that purple vector there is the direction of our motion right now. So just by knowing which way the pressure gradient force and the Coriolis force were, even though they canceled out to 0, by knowing which way they are, you now know which way the wind is blowing? Yep, that's exactly right. Well, that's kind of sounds handy. Okay? Now, we can actually get more information out of this. For example, I've got some forces here, like the pressure gradient force, and, well, gosh, pressure gradient force is all about, how the isobars are spaced. What do I know about the way the isobars are spaced if I have a pressure gradient force that looks like that? Well, actually, they have to be spaced about like what I have there on that on the map there, those little blue lines I put on there. Because I know that pressure gradient force vector, which is that red vector on there, has to be perpendicular to the isobars around it. Well, I think I did a pretty good job for PowerPoint of getting those in there perpendicular. And you have to orient those isobars so that the pressure gradient force vector is pointing toward low pressure. Oh. So see, I got those isobars in there, and I have my pressure gradient force vector, that red vector in there. It's perpendicular to the isobars around it, and it is pointing in the direction of the lower pressure. Okay. Hey, I got all that just from knowing about the forces on that air parcel, even though the forces added up to 0? Yeah. I do want to draw your attention to, by the way, so I have those those pressure contours on there, but notice they're not labeled. I didn't label them like 1,000 millibars, 1,004 millibars. We don't actually know what the values of these pressures are. We just know that that's the way in which the contours of the pressure, but the actual values on there, we can't figure that out yet from this. Okay. But we know that the gradient, at least, has to be pointing that way. Boy, we kind of managed to get a lot of information just knowing a little bit about these two forces. And actually, we can put that information together, combining what we know about the motion of the air, the wind, from what we knew about the Coriolis force, and putting that together with what we know about the pressure pattern from the pressure gradient force. If I just put those two pieces of information on the same map right here, we can see that under the conditions we're talking about here, 1, the wind has to be parallel to the isobars. See how the wind vector, the purple vector there, is parallel to the isobars? And notice which way it blows. It blows so that there is lower pressure to its left and higher pressure to its right. Oh, wait a minute. Let's back up here for a second here. I glossed over saying under these conditions. What do we mean by these conditions? By these conditions, I mean flow that's not being affected by friction, right? Because we got rid of friction in order to make all these assumptions happen. And that's okay in the free atmosphere. We don't have any wind turbines that are up there in the free atmosphere, but this is going to tell us something we're going to build on to start learning about winds down here near the surface. Alright, so under the kind of conditions we would see farther above the ground than a kilometer or two, we are seeing that the winds are going to be parallel to isobars, and they're going to have low pressure to the left of the flow. This is important. This is an approximation. The real wind is not necessary. If you actually went up there and took a measurement using a weather balloon or something like that of what the winds are doing, the exact direction and speed of the wind right now is not necessarily going to be exactly like this. This is an approximation. But it is a really good approximation, as you're going to see. The real winds are going to be pretty close to this. In fact, this approximation is so good that the kind of winds we're drawing on this map is just drawing them as parallel to isobars, low pressure to their left, high pressure to the right. We give them a name. We call those geostrophic winds. Don't get the idea that like, oh look, we're going to go outside and measure the geostrophic wind or something. No, it's something you compute, or it's something you estimate. You know what the pressures look like, and you draw the winds to be parallel to the ice. You get the contours of the pressure, and you draw the winds to be parallel to it. Okay, alright, I see. Geostrophic is a weird word. Your textbook divides the word geostrophic into two Greek pieces, geo and strophic, where the book says geo means earth, and strophic means is turning in like ancient Greek. And this is just a nod to the fact that which of our forces depended on the Earth turning? Oh yeah, the Coriolis force. And so this word geostrophic comes to us from kind of a way of saying it's a force balance that's due to it's an approximation that you make when you're taking into account the Coriolis force. I don't love this division of it up into geo and strophic, because other textbooks divide it up into geos with the S and trophic, and they say something slightly different as to what those means and so on. I don't know what the truth is, to be honest. I've never seen it before this textbook explained this way, but anyway, trope in general, T-R-O-P in general, does have to do with overturning or spinning or something like that. It's whether or not that S should be at the beginning or not. But anyway, I don't care. It's a way of thinking about this word geostrophic. Geostrophic is a way of, this word geostrophic wind is an approximation to what the real winds are doing. But even in the free atmosphere, away from the surface, the real winds are not exactly going to be the same as what you calculate as your geostrophic wind, because there were some assumptions here. We had to make some assumptions, first of all, that there was no net acceleration on the air parcel. Remember, we had to make that assumption? We said that the forces are in balance. The wind was not changing. And we don't love that, but you know, at least if we're just talking about like right this moment, not like between now and tomorrow. This is not a prognostic equation that's going to be telling us about what the winds are doing in the future. This is a diagnostic equation that's telling us about what the winds are, explaining what the winds are doing now, diagnosing what the winds are doing. We also had to make this somewhat crummy assumption that there's no friction. I don't know yet that I'm all that comfortable with either of those. We'll have to make some decisions about that. But let's actually do a little example of what geostrophic winds look like, you know, when we would actually work with a weather map. Now, this is a map I just happen to have on my hard drive that shows the pressure of the atmosphere 3,000 meters above sea level. That's what the little box up there highlights. This is the 3,000 meter pressure. This is not something atmospheric scientists normally would be working with, but I happen to have this from a different teaching demo on there. So these contours on this map are isobars. They're lines of pressure. You can kind of squint and actually see, like the one that goes through Texas and Oklahoma, and so that's the 700 millibar contour, and the one just to its north is the 996 millibar contour, and so on. They're contours of pressure on a weather map, indicating that there's like an area of lower pressure there in the prairie provinces of Canada. There's an area of high pressure over South Florida and so on. And we could actually take that, and at the same time, I used some software to compute the geostrophic wind at about a zillion locations on this plot right here. And I just drew the geostrophic wind there as vectors at each location, where the size of the vector tells us something about the speed of the geostrophic wind approximation, and you know, the winds we are approximating using the geostrophic wind approximation. And okay, well, if I it's kind of cluttered on this plot here, so if I use my magnifying glass here to zoom in on, I guess I have got Illinois and Indiana there, that will help you see a good example. If you can still see those white contours on there showing us the isobars, you can see how the geostrophic winds are parallel to those isobars. Fantastic. And in fact, once you see that pattern to it, feel free to go over there and squint at every little corner you feel like looking at, and you'll see that the winds are always parallel to these isobars on this map of the geostrophic wind. And what else I'm noticing on this plot, though, is that, boy, there are vectors that are long and there are vectors that are short. I see that the geostrophic wind is varying a lot from one place to another. Why is that? We didn't yet talk anything about this geostrophic approximation in terms of what is it telling us about the speed of the wind. Well, let's go back and look again at this map I was making of, you know, an air parcel positioned someplace over central Nebraska. And I had some isobars there, so I could see which way my pressure gradient and my pressure gradient force were. What determined the magnitude of the pressure gradient force again? Oh yeah, it was about how close together the isobars were. The closer the isobars got together, the stronger the pressure gradient force, because the pressure gradient was getting bigger. The change in pressure over a distance. So if I took those same, you know, that same situation there, but I put twice as many isobars there, my pressure is changing more over a smaller distance. My isobars are getting really close together. So like in this case, I doubled how close together the isobars were. So I doubled the pressure gradient force. Well, I said under my assumptions here, we're saying that the pressure gradient force will be equal and opposite to the Coriolis force. So if my pressure gradient force has doubled, I guess my Coriolis force doubled too. Oh yeah, I drew it bigger there. Now what determines the strength of the Coriolis force? Well, okay, it's true that latitude is part of the story, but I'm not changing the latitude. One of my things I'm not doing here is I'm not moving Nebraska to a different latitude. At the latitude I've got to work with, the only other thing that controls the strength of the Coriolis force is the speed of the wind. So if I want to have a bigger, stronger Coriolis force, I've got no choice but to speed the wind up. So I end up with a stronger wind when the isobars are closer together, and a weaker wind when the isobars are farther apart. Now, the mathematics and the physics of actually deriving why that has to be and so on, that's not what this class is about. I just want you to see this pattern here. See how when the isobars were far apart, the wind was slow, and when the isobars are close together, the wind was stronger, like up there in the top right corner? Here's how I like to picture it. Picture a hose. Okay? When the hose is wide and fat, the water moves through the hose slowly, and when the hose gets narrower and narrower, the flow goes through it faster. Think of it as like the space between each of these isobars on this map as being kind of like a little hose. Okay? When this gap between there is wide, the flow is slow, but when they get closer and closer together, the flow gets stronger and stronger. Now, in fact, it works nothing like that, but the pattern is right. Okay? That's a way to picture it in your mind. So, when we're thinking about this geostrophic wind, let's actually say that it's an approximation to what the real wind or the observed winds are doing, and it says that the flow should be parallel to isobars, with low pressure to the left of the flow. That's actually only true in the northern hemisphere. It'd be to the right in the flow than the southern hemisphere, but let's not worry about the southern hemisphere right now. And the flow should be stronger when the isobars are closer together, and the flow should be weaker when the isobars are farther apart. Okay, let's see if that jives with what I actually had here on my map. So here's my map here, and I've got some geostrophic wind vectors, as you recall, and I've got some pressure contours on there, some isobars, and if I just use my little magnifying glass on there and kind of zoom in here on, I don't know what that is, I guess that's northeast New Mexico and so on, I can see that these places over here where the isobars are pretty far apart, my wind vectors are really short. But if I go over here to say, southeast Missouri and southern Illinois and so on, where the isobars are much closer together, my speed of my geostrophic wind gets stronger and stronger. Oh. Well, that's pretty cool. In fact, you can feel free, again, to flip back and forth between different slides and see how well the pattern holds up. That's really cool. It's really cool, actually, because not only is this a powerful tool, I mean, I can just look at a map with my puny human eyes, and I can see things like contours of pressure on this map. Here they're far apart. Here they are close together. Therefore, where they are close together, there will be stronger winds. Where they are farther apart, there will be weaker winds. No matter whether I am talking a place where they're close together or far apart, the wind will be parallel to the isobars, and it will have lower pressure to its left. All of this sounds really powerful. In fact, it's mathematically powerful too. I mean, if I zoomed in further here onto this white blob over here is just like northeast Nebraska. This is actually all mathematically robust. We could actually have derived this whole thing, except it's no fun whatsoever. But we could actually take that vector, I mean, the geostrophic wind is a vector, it has direction and speed, and we would call that vector Vg for velocity, and the G means geostrophic. And in fact, if you take a look at that vector there, you can see, like any vector, you can add it up as in component form. You could say that there's a component in the x direction and there's a component in the y direction. The component in the x direction is called Ug, for the U wind in the geostrophic direction, I'm sorry, the geostrophic wind in the U direction, U being the X direction there, and Vg, that's a little v, I know the notation gets a bit confusing, is the component in the north-south direction. Okay, and in fact, by the way, it can actually be nicely derived mathematically. Again, no fun whatsoever, but we could actually compute those components, Ug and Vg, and all it takes there is F, which is Coriolis parameter, and that's a rho. We'd have to know the density of the air. And then, oh crud, partial derivatives. The partial derivative of pressure with respect to y. And there's a partial derivative with the pressure with respect to x in the bottom equation there for Vg. Oh no. But remember, we actually have a trick to get around that partial derivative thing. We could actually say that close enough, we could use this differencing method where we had like the difference between the pressure to the north and the pressure to the south, or the pressure to the east and the pressure to the west. In fact, I could actually illustrate that over here on our map. If I wanted to actually compute the geostrophic wind vector at that green central location there, I just needed to know the pressure at a place to its north and a pressure at a place to its south. And I also need to know the pressure at a place to its east and a pressure at a point to its west. And you have to know the distance between those points, that's delta x and delta y. But you know what, it's all doable. And it's a pretty good approximation. And we could actually come up with what, and that's what, when I showed you all those wind vectors and stuff, that's really what the software did, is it just did this calculation on what the pressure needed to be, what the pressure is, what the U and the V components of the geostrophic wind were. Oh, I can live with that. Okay, this geostrophic wind approximation is pretty slick. I can see how this is easy to work with. But is it any good? Is it anything like what the real wind is actually doing? And the answer to that is absolutely, because I've been lying to you. Dr. Schragi loves to lie to students. There's nothing better than lying to students and then straightening it out as a teaching tool. And I've been lying to you all along. This map I've been showing you, that's not geostrophic winds at all. That's real winds from observations. And the reason why I showed it to you is because the real winds are practically exactly the same as the geostrophic wind. It's such a good approximation. In fact, as long as, one, we're talking about winds that are above the top of the boundary layer, that is to say, in the free atmosphere, and two, that we're in a situation where the winds aren't changing rapidly. We're not like in a landfalling hurricane or in the updraft of a tornado or something. Okay. No, if we're just in a situation where the winds are not changing all that rapidly and we're outside the boundary layer where we have to worry about all the friction crap, then the geostrophic wind approximation is actually so incredibly good, we can hardly tell the difference between the observed winds that, like, a weather balloon would be coming up with, or the geostrophic approximation to the winds. They look pretty much identical, okay? In fact, they won't be exactly the same. Again, if I zoomed back in on northeast Nebraska here, that's what the blob is. If I actually did the math and I actually came up with exactly what is the geostrophic wind, VG, it would be like a purple vector, let's say, right there. And let's say I launched a weather balloon at that exact location and I got that the wind at that location, you know, at whatever height up or whatever was that red vector, V. And they're pretty darn close. They're about 10 degrees separate, is how I drew it. They're probably not exactly the same, okay? But they're pretty darn close. But actually there is a small difference, and in fact there is a little vector difference between the two there. You can see I put it in there. It's VAG, the ageostrophic wind. Boy, that's a hard word. Ageostrophic. Okay. The ageostrophic component of the flow will be that little difference between the geostrophic approximation and the real wind. In fact, a mathematically nice way to put it is to say, like I'd have in that little vector equation down there, that the geostrophic wind plus the ageostrophic wind is equal to the real wind that you would observe. And as you can see on this diagram here, I mean, VAG is tiny compared to VG and V. In fact, in the real atmosphere, most of the time the measuring error associated with measuring the real wind is actually bigger than the ageostrophic component of the wind. Most of the time, to within the error bars of what we actually know the speed and direction of the wind, the geostrophic wind and the real wind, the observed wind, are the same. Okay, we don't measure wind so super accurately away from the surface of the Earth anyway. In other words, that geostrophic assumption or the geostrophic approximation, that is a really good one. Let me tell you what, in the atmospheric sciences, not that many things approximate that easily. The geostrophic assumption is like this brilliant thing that makes every atmospheric science major's heart swell, that something actually, damn it, worked, okay? This actually works really well, and as long as we stick with these assumptions, that the winds aren't changing all that much, and so we can say that the change in the speed is equal to 0, and therefore there's no acceleration, and so on. Okay, as long as we can live with that part of the assumption, which it turns out is not so bad, and we can say that there's no friction, geostrophic assumption, or the geostrophic approximation, or the geostrophic wind, is actually pretty much the same thing as real winds, as long as those assumptions apply. But bummer, those assumptions don't apply in the boundary layer, because we've got friction. Remember, the boundary layer, kind of by definition, that lowest kilometer or two of the atmosphere, is where the effects of friction with the surface are being felt. We don't get to throw friction out. We don't get to get rid of... Oh, crud. Turns out that's not such a big deal. We're going to build on what we learned from geostrophic wind to help us with this. Because, see, this is where the wind turbines are. If we're going to learn about wind power, we're not going to get to know that much about geostrophic wind, but actually don't let it be that discouraging. Because the winds in the boundary layer are not completely unrelated to geostrophic wind. What we're going to do with our idea of geostrophic wind when we start talking about the boundary layer is we'll start adding friction. And we'll see how that changes all of this. It's just tweaking it. And then the geostrophic winds are telling us important things about the weather patterns, like cyclones and jet streams and things like that we're going to be learning throughout the rest of this module. So it's not really such a bad thing to have, like, well, you know, it's like we have any turbines up there at the level where the winds are geostrophic anyway. Trust me, we'll get this figured out. All right. Oh, man. Geostrophic wind is such a powerful tool. There's so many cool meteorology things we could do with it. And we will be doing more things with it over the course of the semester, but for now, let's answer a couple questions about it. Question 4. The geostrophic wind is a good approximation to what observed winds look like in the free atmosphere. True or false? Okay, answer that question, follow one of the 2 links, get some feedback before you move on to question 5.